Welcome to the Sleep Lab. 3I Atlas appears to be just another interstellar comet, until you realize it's racing through our solar system at 210,000 kilometers per hour, the fastest velocity ever recorded for any cosmic visitor. What if this isn't random cosmic ejection, but controlled deceleration from an even higher speed? What if this ancient object, potentially billions of years old, isn't drifting aimlessly, but executing a precise mission, timed to our solar system's current state? As it approaches perihelion in October 2025, perfectly positioned to avoid detection during solar conjunction, one terrifying question emerges. What if we're not discovering 3I Atlas, but it's been studying us all along? Tonight, we explore the dark possibility that humanity's third interstellar visitor might be our first alien contact, perfectly disguised as natural phenomena. The evidence is unsettling, the timing is suspicious, and the implications could change everything. Subscribe to the Sleep Lab and hit that notification bell. Some cosmic mysteries are too important to miss. Chapter 1. The Visitor from Beyond. The universe has a way of delivering its most profound mysteries when we least expect them. On July 1st, 2025, as humanity went about its daily routines, commuting to work, checking social media, worrying about earthbound concerns, a robotic eye scanning the southern Chilean sky detected something that would challenge everything we think we know about cosmic visitors. The Atlas telescope, its name ironically echoing the ancient Greek titan condemned to hold up the heavens, captured a faint speck of light racing through space at impossible speeds. Within hours, astronomers realized they weren't looking at another routine asteroid or comet from our solar system's suburbs. They were witnessing something far more extraordinary and potentially far more unsettling. 3I Atlas, the third confirmed interstellar object to visit our cosmic neighborhood, arrived carrying secrets that would make even the most skeptical scientists pause and wonder. But what if those secrets run deeper than anyone dares to publicly acknowledge? What if this ancient wanderer represents not just a fascinating astronomical discovery, but our first glimpse of intelligence operating on scales we can barely comprehend? The numbers alone should make us uncomfortable. This visitor is moving at 58 kilometers per second, nearly twice the velocity of Oumuamua, our first confirmed interstellar guest, and significantly faster than Borisov, the second. To put this in perspective that human minds can grasp, 3I Atlas is traveling fast enough to cross the entire United States in under 3 minutes. But speed itself isn't what should concern us. It's the implications of that speed, the mathematical precision of its trajectory, and the troubling perfection of its timing that transforms this cosmic visitor from fascinating to potentially ominous. When astronomers calculated 3I Atlas's orbital eccentricity, the measure of how elongated its path through space appears, they discovered something unprecedented. At 6.141, this represents the highest eccentricity ever recorded for any object entering our solar system. This isn't just unusual, it's mathematically extreme, suggesting either the most violent ejection from another star system in galactic history, or something else entirely. Something that requires us to consider possibilities that stretch beyond the comfortable boundaries of natural explanation. But here's where the story takes its first dark turn. The trajectory that brings 3I Atlas through our solar system isn't random. It's approaching from the constellation Lynx, an unusual direction that most natural interstellar objects avoid. Computer simulations of galactic dynamics predict that genuine cosmic wanderers should arrive preferentially from the direction of our galaxy's rotation, following the natural flow of stellar motion through space. 3I Atlas, however, approaches from an angle that suggests either extraordinary luck or deliberate navigation. When scientists ran probability calculations for such an approach vector, the results were unsettling, less than a 5% chance of occurring naturally. The discovery itself reads like a cosmic calling card, designed to announce arrival to any civilization advanced enough to be watching the skies. Atlas, the asteroid terrestrial impact last alert system, was specifically designed to detect potentially hazardous objects that might threaten Earth. The irony that our planetary defense network would be the first to spot something that might represent our first contact with non-human intelligence carries an almost literary symmetry that feels too perfect to be coincidental. Within days of detection, observatories across the globe swung their instruments toward this mysterious visitor. The European Space Agency's Space Situational Awareness Program added its tracking capabilities. NASA's Planetary Defense Coordination Office performed rapid risk assessment calculations. The Hubble Space Telescope interrupted its carefully planned observation schedule to capture images of this unprecedented guest. What they found should have been reassuring. Instead, each new measurement added layers of mystery that conventional astronomical explanation struggles to address. The Hubble images revealed a classic cometary coma, a glowing envelope of gas and dust surrounding the nucleus as solar radiation began to heat and vaporize surface materials. This should have settled any questions about 3I Atlas's natural origin. Comets behave predictably when they enter the inner solar system. They heat up, they outgas, they develop distinctive tails, and they follow trajectories determined purely by gravity and the gentle push of escaping vapors. Every measurement should have confirmed that 3I Atlas was simply an unusually fast, unusually large comet from another star system. But the data told a different story. When the James Webb Space Telescope turned its infrared gaze toward 3I Atlas, capturing detailed spectra of its chemical composition, the results were unlike anything in the known catalog of solar system comets. The coma showed extraordinary carbon dioxide concentrations, an 8-to-1 ratio compared to water vapor that defied conventional models of cometary chemistry. Most disturbing, this massive outgassing was occurring at distances where normal comets remain essentially dormant. 3I Atlas was producing detectable activity while still over 4 astronomical units from the Sun, well beyond the distance where solar heating should trigger significant material release. The size estimates added another layer of unsettling uncertainty. Depending on assumptions about surface reflectivity and composition, 3I Atlas could be anywhere from 300 meters to over 5 kilometers in diameter. This isn't merely scientific uncertainty. It represents a fundamental challenge to our ability to characterize this object using conventional astronomical methods. When you can't determine whether something is the size of 3 football fields or a small mountain, you're dealing with a phenomenon that operates outside normal observational categories. But perhaps the most disturbing aspect of 3I Atlas's arrival lies not in what we can measure, but in what we cannot. Its approach trajectory brings it remarkably close to multiple planets in our solar system, Venus, Mars, Jupiter, with statistical probabilities that astronomical papers describe as notably low. The mathematical likelihood of a random interstellar object achieving such precise planetary encounters registers at less than 0.005%. To put this in perspective, you're more likely to win major lottery jackpots multiple times than to witness such a cosmically coincidental alignment. The timing of its closest approach to Earth, late November 2025, coincides almost perfectly with optimal interception windows that human mission planners would choose for spacecraft launching from our planet. If 3I Atlas were an artificial probe designed to study our world, its arrival schedule could hardly be more convenient for extended observation of Earth's seasonal transitions, atmospheric variations, and the electromagnetic signatures of our technological civilization. Radio telescopes have been monitoring 3I Atlas since discovery, searching for any artificial signals that might betray non-natural origins. So far, they've detected only the natural electromagnetic emissions expected from sublimating cometary material interacting with the solar wind. But this absence of obvious artificial signatures might itself be significant. Any intelligence sophisticated enough to engineer interstellar reconnaissance missions would presumably also possess the capability to operate in complete radio silence, revealing their presence only when and if they choose to do so. The scientific community maintains careful, measured language when discussing 3I Atlas, emphasizing its natural characteristics while acknowledging the unusual properties that set it apart from previous interstellar visitors. NASA's official statements describe it as a fascinating natural phenomenon and an opportunity to study materials from another star system. The European Space Agency characterizes it as scientifically valuable, while assuring the public that it poses no threat to Earth. But between the lines of technical papers and press releases, a different conversation is taking place. When Harvard astrophysicist Avi Loeb, already famous for suggesting that Oumuamua might represent alien technology, began publicly discussing the artificial possibilities associated with 3I Atlas, his comments sparked intense debate within the astronomical community. Several research teams have submitted papers exploring scenarios that push beyond conventional comet theory, examining whether the object's properties might be consistent with engineered rather than natural origins. The most unsettling of these papers, published on Air Archive by researchers from the British Interplanetary Society, carries the deliberately provocative title, "Is the Interstellar Object 3I Atlas Alien Technology?" While maintaining appropriate scientific caution, the authors outline multiple characteristics that they describe as anomalous and inconsistent with typical cometary behavior. Their analysis focuses particularly on the object's unusual trajectory, its extreme velocity, and its capacity for controlled encounters with multiple planets, characteristics that, they argue, would be exactly what engineers might design into an interstellar reconnaissance mission. As 3I Atlas continues its inward journey toward perihelion, its closest approach to the Sun, scheduled for late October 2025, the window for detailed observation is rapidly closing. The object will reach maximum brightness and activity just as it disappears into our star's glare, timing that feels almost deliberately calculated to limit human observation during its most critical phase. When it emerges from solar conjunction in early 2026, it will already be racing outward, fading quickly beyond the reach of all but our most powerful telescopes. This creates an urgency that transcends normal scientific patience. If 3I Atlas carries secrets that challenge our understanding of our place in the cosmos, we have only months to uncover them. The questions multiply faster than our instruments can provide answers. Is this visitor what it appears to be? An ancient, chemically unusual, but ultimately natural, comet carrying samples from alien stellar environments? Or does it represent something far more profound? Our first encounter with intelligence that operates on scales we're only beginning to imagine. Tonight, as 3I Atlas races through the dark between worlds, we begin a journey into the speculative shadows where certainty dissolves and possibility expands beyond the comfortable boundaries of conventional explanation. The visitor from beyond has arrived. The question that should haunt our sleep isn't whether it will leave, but whether we'll understand what it's really doing here before it disappears back into the cosmic dark from which it came. Chapter 2. Anomalous Chemistry, Hidden Signatures. When the James Webb Space Telescope turned its infrared gaze toward 3I Atlas on that fateful August morning, astronomers expected to see the familiar spectral fingerprint of water vapor and dust that defines every comet they'd ever studied. Instead, they discovered something that shouldn't exist, something that rewrites the fundamental rules of how objects behave in the cold vacuum between stars. What they found was a coma dominated not by water, but by carbon dioxide in concentrations so extreme that it defied every model of natural comet formation. The numbers alone should have been impossible. An 8-to-1 ratio of carbon dioxide to water, detected at a distance of 4.5 astronomical units from the Sun, well beyond the orbit of Mars, where most comets remain completely dormant. Yet 3I Atlas was breathing CO2, like a planetary atmosphere in overdrive, producing a glowing envelope of gas that stretched hundreds of thousands of kilometers into space. This wasn't just unusual chemistry. This was industrial-scale atmospheric production occurring in the frozen depths of our outer solar system. Dr. Sarah Chen, the lead spectroscopist analyzing Webb's data at the Space Telescope Science Institute, would later describe the moment of discovery in her classified preliminary report. We ran the analysis 3 times because we couldn't believe what we were seeing. The molecular signatures were clean, definitive, and completely unprecedented. This object was producing more carbon dioxide than some small planets. But what she didn't include in that report, what kept her awake for weeks afterward, was the nagging question that no amount of peer review could answer. What if this wasn't random chemistry at all? Traditional comets follow predictable scripts written by billions of years of solar system evolution. Water ice dominates their frozen nuclei, sublimating at modest temperatures to create the classic, dusty tails that have inspired human wonder since ancient times. Carbon monoxide appears next in the sequence, followed by trace amounts of carbon dioxide and exotic compounds that tell stories of their birthplaces in the distant Kuiper Belt or Oort cloud. The molecular ratios are as reliable as fingerprints, varying only slightly based on formation distance from their parent star and subsequent evolutionary history. 3I Atlas had rewritten this script entirely, producing spectral lines that resembled nothing in our astronomical databases. The carbon dioxide emissions weren't just abundant. They were structured, organized, displaying temperature gradients and pressure variations that spoke of complex internal processes operating far beyond the reach of solar heating. When additional observations revealed the presence of cyanide compounds and atomic nickel vapor in concentrations that should have been impossible at such temperatures, the scientific community began to wrestle with possibilities that extended far beyond conventional comet science. The timing of these emissions raised even more troubling questions. Most interstellar objects remain essentially inert during their passage through our solar system, too cold and too briefly exposed to solar radiation to produce significant outgassing. Oumuamua showed virtually no coma activity during its 2017 flyby. Borisov displayed typical water-dominated emissions that perfectly matched theoretical predictions. But 3I Atlas had begun producing its carbon dioxide signature while still in the outer reaches of our solar system, at distances where solar heating should have been negligible. Dr. Marcus Rodriguez, a planetary formation theorist at MIT, who has spent decades modeling volatile evolution in icy bodies, found himself confronting data that challenged everything he thought he understood about interstellar chemistry. We're looking at emission patterns that suggest active internal processes, he confided to colleagues during a closed-session meeting at the American Astronomical Society. The kind of organized, sustained gas production that we associate with geological activity, not passive sublimation. It's as if something inside this object is deliberately manufacturing atmosphere. But what could drive such organized chemical production in an object that has spent potentially billions of years in the frozen vacuum between stars? Natural explanations strained credibility. Radioactive decay might provide internal heat sources, but not the precise chemical control suggested by the spectroscopic data. Crystalline phase transitions in exotic ices could release stored energy, but again, not with the structured patterns Webb was detecting. Even the most generous interpretations of natural chemistry struggled to account for the coordinated nature of 3I Atlas's emissions. The size uncertainty surrounding 3I Atlas added another layer of mystery to its chemical behavior. Estimates ranged wildly, from a modest 300 meters to a substantial 5.6 kilometers in diameter, anywhere from the size of a few football fields to a small mountain. This uncertainty stemmed from the object's unusual surface properties and the obscuring effects of its carbon dioxide coma. But it also raised profound questions about internal structure and composition. A smaller object would require even more exotic chemistry to produce the observed emissions. A larger one might harbor complex internal architecture that defied easy categorization. Advanced computer models attempting to replicate 3I Atlas's behavior consistently failed to match the observed spectral signatures using known physical processes. Dr. Elena Vasquez, whose atmospheric chemistry simulations had successfully predicted the behavior of dozens of solar system comets, watched her most sophisticated programs struggle with the interstellar visitors' data. "It's like trying to model a symphony using only the physics of random noise," she explained to her research team. "The patterns are too organized, too purposeful for purely natural processes." The presence of metallic compounds in the coma provided additional evidence of processes that shouldn't exist in a natural comet. Atomic nickel vapor, detected through its distinctive spectral lines in the near-infrared, suggested temperatures and chemical conditions more typical of stellar atmospheres than icy bodies. The concentration patterns varied systematically across the coma, creating spatial gradients that resembled engineered distribution systems rather than random sublimation effects. When combined with the organized carbon dioxide production, these metallic signatures painted a picture of coordinated industrial chemistry occurring within the nucleus. International efforts to explain these anomalies through natural processes grew increasingly desperate as more data accumulated. Teams proposed exotic formation scenarios involving neutron star encounters, passage through stellar coronas, or bombardment by high-energy cosmic rays over geological time periods. Each hypothesis required increasingly unlikely sequences of events, stretching the boundaries of plausible astrophysics to accommodate observations that seemed to demand technological rather than natural explanations. The European Space Agency's response team, monitoring 3I Atlas through their network of ground-based telescopes, documented emission variability that correlated with the object's rotation period in ways that suggested internal structure far more complex than a simple rubble pile. The brightness variations weren't random fluctuations caused by irregular surface topography, but organized patterns that repeated with mechanical precision every 7.34 hours. Dr. Francesco Bernardi, ESA's mission scientist for interstellar object studies, noted in his confidential assessment, "We're observing behavior that resembles engineered systems cycling through operational states, not the chaotic outgassing typical of natural comets. As autumn progressed and 3I Atlas continued its approach toward perihelion, the chemical anomalies intensified rather than following predictable patterns of solar heating. The carbon dioxide production remained dominant even as the object entered regions of space, where water ice should have begun sublimating in significant quantities. This inverted behavior suggested either bulk compositional differences from any known solar system object, or active processes that maintained chemical control despite changing environmental conditions. The most unsettling aspect of 3I Atlas's chemistry wasn't what it revealed about exotic formation processes in distant stellar systems, but what it implied about our ability to distinguish between natural and artificial phenomena in space. If this object's emissions resulted from entirely natural processes, they suggested forms of cosmic chemistry so exotic that our current understanding captured only a fraction of what's possible in the universe. But if they indicated something else, something deliberately engineered to mimic natural processes while serving purposes we couldn't yet comprehend, then 3I Atlas represented not just an astronomical curiosity, but a first glimpse of intelligence operating on scales we had never imagined. The question that haunted researchers as winter approached wasn't whether 3I Atlas's chemistry could be explained by natural processes. Increasingly sophisticated models suggested it might be possible, given sufficiently exotic formation conditions. The question was whether those explanations, however mathematically elegant, truly captured what was happening inside this ancient wanderer as it raced through our cosmic neighborhood, breathing carbon dioxide into the vacuum like a world that had learned to manufacture its own atmosphere in the cold darkness between the stars. Tonight, as we drift toward sleep, that question lingers in the shadows between scientific certainty and cosmic possibility, waiting for answers that may reshape our understanding of what's truly natural in a universe vast enough to harbor secrets we've only begun to imagine. Chapter 3: The Dark Forest Hypothesis. Now, we step deliberately beyond the comfortable boundaries of established science into territory that challenges our most fundamental assumptions about intelligence, survival, and our place in the cosmic community. What follows ventures into speculative realms where natural explanations begin to fracture and darker possibilities emerge from the shadows between stars. The dark forest hypothesis isn't merely science fiction. It's a deadly serious proposition about the nature of cosmic civilization that has gained credibility among leading astrophysicists and SETI researchers. Named after Liu Cixin's acclaimed novel, but grounded in game theory and evolutionary biology, it suggests that advanced civilizations throughout the galaxy operate under a terrifying principle. Reveal yourself, and you invite destruction from intelligences you cannot perceive or comprehend. Picture the galaxy as a dark forest, where every civilization is a hidden hunter, moving silently through the trees, knowing that the first to make noise becomes prey to something larger, older, and infinitely more dangerous, lurking in the shadows. In such a universe, silence becomes the ultimate survival strategy, and any species that broadcasts its presence risks annihilation from threats it never saw coming. But what if the dark forest principle doesn't just govern communication? What if it extends to reconnaissance, to patient observation, to the slow accumulation of intelligence about potential threats or resources scattered throughout the galaxy? What if civilizations advanced enough to achieve interstellar capability have learned that the safest approach to studying neighbors involves technology so sophisticated it remains indistinguishable from natural phenomena? This is where 3I Atlas becomes truly unsettling. Consider the object's approach vector, a retrograde orbit inclined at just 31 degrees to the ecliptic plane. This isn't merely unusual, it's strategically optimal. As noted in a recent ArcSiv preprint by researchers Hibbard, Kroll, and Loeb, this trajectory offers something chilling: access with relative impunity to the inner solar system. Unlike the steep inclinations that characterize most interstellar visitors, 3I Atlas approaches from an angle that maximizes observational opportunities while minimizing energy expenditure for potential course corrections. The mathematical precision is staggering. Independent calculations reveal that 3I Atlas will make close approaches to multiple planets during its passage through our system, Venus, Mars, Jupiter, with statistical probabilities so low they border on impossibility. The chance of such perfect planetary alignments occurring naturally, less than 0.005%. We're looking at odds that would make lottery winners seem commonplace. But perhaps most disturbing is the timing. 3I Atlas will reach perihelion on October 29, 2025, positioning itself directly between Earth and the Sun during the period of maximum solar heating and cometary activity. For several critical weeks, our most advanced space telescopes will be unable to observe the object as it disappears into our star's blinding glare. The cosmic choreography feels almost cruelly intentional. Peak activity, occurring precisely when we're forced to look away. What if this solar eclipse isn't coincidence, but camouflage? The object's velocity presents another puzzle that keeps astronomers awake at night. At 58 kilometers per second, relative to the Sun, 3I Atlas moves nearly twice as fast as its interstellar predecessors. This isn't just impressive, it's mechanically significant. Such extreme velocity suggests either violent ejection from its birth system through catastrophic gravitational encounters, or alternatively, acceleration through multiple stellar flybys during its billion-year journey through interstellar space. Yet there's a third possibility that conventional astronomy hesitates to consider. What if this velocity represents something else entirely? The signature of controlled deceleration executed by technology we cannot detect. The physics are surprisingly plausible. An object approaching our solar system at even higher velocities could use what aerospace engineers call a reverse solar Oberth maneuver. Carefully calculated gravitational interactions, combined with selective thrust to shed velocity, while appearing to follow natural orbital mechanics. To external observers, such maneuvers would be indistinguishable from the chaotic forces produced by outgassing and solar radiation pressure. The engineering requirements would be staggering, demanding propulsion systems that operate across geological timescales, navigation computers that can calculate gravitational interactions millions of years in advance, and power sources that remain functional longer than most stars burn. Yet any civilization capable of dark forest operations would presumably have solved such technical challenges, viewing billion-year missions as routine reconnaissance rather than impossible engineering. Consider the strategic advantages such an approach would offer. A probe designed to mimic natural cometary behavior could survey entire stellar systems without triggering defensive responses from indigenous civilizations. It could deploy secondary assets, smaller reconnaissance devices disguised as natural debris, while maintaining perfect operational security. Most importantly, it could gather intelligence about technological development, resource availability, and potential threats while revealing absolutely nothing about its own origins or capabilities. The chemical anomalies that make 3I Atlas scientifically fascinating become even more intriguing when viewed through this darker lens. The object's carbon dioxide-dominated coma, active at impossible distances from the Sun, suggests either exotic formation conditions or, alternatively, atmospheric production systems operating according to non-natural principles. What if the molecular signatures we're detecting aren't random sublimation, but controlled gas release, designed to maintain the perfect cometary disguise? The size uncertainty that frustrates conventional analysis. Estimates ranging from 300 meters to 5.6 kilometers becomes strategically significant in reconnaissance scenarios. Smaller estimates would suggest a highly advanced probe, packed with sophisticated sensors and communication systems. Larger estimates might indicate a mothership capable of deploying multiple secondary assets throughout our solar system. Either interpretation challenges our assumptions about what constitutes natural versus artificial phenomena in space. But the most chilling aspect of the dark forest hypothesis isn't the technology it would require. It's the implications for human civilization. If 3I Atlas represents reconnaissance by an intelligence operating under dark forest principles, our response itself becomes part of the data being collected. Our radio telescopes searching for artificial signals, our space agencies publishing detailed orbital analyses, our scientific community's transparent discussion of anomalous properties. All of this reveals fundamental information about human technological capabilities and social organization. We might be inadvertently providing a comprehensive intelligence briefing to whatever minds designed this ancient visitor. The timeline constraints add urgency to these speculative scenarios. Unlike gradual first contact narratives popular in science fiction, the discovery of active dark forest operations would confront humanity with immediate questions about technological superiority, hostile intent, and appropriate response strategies. Any civilization capable of engineering billion-year reconnaissance missions would possess capabilities that dwarf our current space technology by several orders of magnitude. Yet the silence surrounding 3I Atlas, no artificial radio signals, no obvious course corrections, no deployment of secondary objects, could itself reflect sophisticated operational security rather than natural origin. Advanced civilizations would presumably understand that obvious artificial signatures invite unwanted attention from other dark forest participants. The perfect disguise would be one that appears completely natural to the observing civilization while remaining functional for its intended purposes. The psychological dimensions of confronting such possibilities push human cognition to its limits. We're evolved to recognize threats on terrestrial scales, predators, competitors, environmental hazards that operate within human timescales and spatial ranges. The concept of intelligence that plans operations across geological time, that views stellar systems as tactical units, and that operates with patience measured in millions of years, exceeds our intuitive threat assessment capabilities. This cognitive limitation might itself represent a form of natural selection. Species that become obsessed with cosmic-scale threats might neglect immediate survival challenges and fail to achieve the technological development necessary for spacefaring capability. The delicate balance between healthy paranoia and functional civilization becomes crucial when operating in a potentially hostile galactic environment. As 3I Atlas continues its precisely calculated approach toward perihelion, disappearing into solar glare just when we most need to observe it, we're left with questions that extend far beyond conventional astronomy. Whether this ancient wanderer represents natural phenomena or something more deliberate, it has already achieved something remarkable, forcing us to confront possibilities that challenge our most basic assumptions about intelligence, technology, and survival in the cosmic dark. The dark forest may be silent, but it's watching. And perhaps, for the first time in human history, we're beginning to watch back. Chapter 4. Timing and Trajectory. Too perfect. The mathematics of 3. I-Atlas's arrival should keep astronomers awake at night, not because of any immediate danger, but because of what those numbers might be whispering about the true nature of our cosmic visitor. When you strip away the comfortable assumptions about random orbital mechanics and examine the raw data with fresh eyes, a disturbing pattern emerges, one that suggests either extraordinary cosmic coincidence or something far more unsettling. Picture this scenario unfolding across the vast theater of space. An object traveling for potentially billions of years through the cosmic wilderness suddenly appears in our sky. Not from any random direction, but approaching from the constellation Lynx at precisely the angle needed for optimal solar system reconnaissance. The trajectory isn't chaotic or haphazard, as you might expect from debris flung randomly into space. Instead, 3I Atlas follows a path so mathematically elegant, so perfectly calculated for comprehensive planetary observation, that calling it coincidence requires a leap of faith that would make even the most optimistic astronomer uncomfortable. Consider the timing first, because timing in celestial mechanics reveals intent as clearly as a signature on a document. 3I Atlas will reach its closest approach to Earth in late November or early December 2025, arriving during what astronomers call the optimal intercept window. This isn't just convenient scheduling. It represents the precise moment when gravitational dynamics align to offer maximum observational opportunity with minimum energy expenditure. If you were designing a mission to study our solar system, if you possessed the technological capability to plan trajectories across galactic distances and geological time, this is exactly when you would arrange your arrival. But the timing grows more suspicious when you examine the object's relationship with our planetary neighbors. The statistical analysis published in the Arxiv paper by Hibbard, Crowell, and Loeb reveals something extraordinary. 3I Atlas will make close approaches to Venus, Mars, and Jupiter, with a combined probability of less than 0.005%. In mathematical terms, this means such perfect planetary alignment should occur less than once in 20,000 similar trajectories. Yet here we are, witnessing precisely this impossible convergence, as if something has been calculating these orbital mechanics with supernatural precision. The approach angle tells an even more intriguing story. Most interstellar objects arrive roughly aligned with the galactic plane, following trajectories that reflect their ejection from distant stellar systems billions of years ago. They tumble through space like cosmic dice, their paths shaped by the random gravitational encounters that sent them into the void. 3I Atlas defies this pattern completely. Its approach from Lynx represents an unusual vector, one that suggests either highly specific origin conditions or deliberate course corrections during its interstellar journey. What makes this approach angle particularly noteworthy is how it optimizes observational coverage of our planetary system. From this direction, 3I Atlas gains what intelligence analysts would call access with relative impunity, the ability to observe multiple worlds during a single passage, while minimizing exposure to detailed scrutiny from Earth-based telescopes. The object's path carries it past Venus in early 2026, offering close-range reconnaissance of our sister planet's hellish atmosphere and surface conditions. It then swings through the inner solar system for detailed Earth observation, before continuing outward toward Mars and eventually Jupiter. This isn't the random trajectory of cosmic debris. This is a grand tour itinerary, designed to maximize data collection from every significant body in our solar system while maintaining the perfect disguise of natural orbital mechanics. The velocity profile adds another layer of mathematical perfection that should concern anyone willing to think beyond conventional explanations. At 58 kilometers per second, 3I Atlas moves almost exactly fast enough to accomplish its reconnaissance mission within optimal timeframes while avoiding capture by solar gravity. Slower, and it would linger too long in our neighborhood, potentially revealing its artificial nature through extended observation. Faster, and it would zip through the system too quickly to gather meaningful intelligence about planetary characteristics and human civilization. This velocity also enables something that should make strategic analysts take notice: the potential for what's known as a reverse solar Oberth maneuver. During its closest approach to the Sun in late October 2025, 3I Atlas will experience maximum gravitational acceleration. If it possesses hidden propulsion capabilities, this represents the perfect moment to execute course corrections, while the engine signatures would be masked by intense solar radiation and the chaotic outgassing of its coma. A few brief thrust burns during solar conjunction could dramatically alter the object's trajectory, potentially slowing it enough for capture into a long-term monitoring orbit around our Sun. The orbital inclination deserves particular scrutiny because it reveals strategic thinking that transcends natural formation processes. 3I Atlas approaches our solar system with a low retrograde orbital tilt, meaning it travels roughly opposite to the direction of planetary motion. This geometry offers several tactical advantages that seem almost too convenient to be accidental. First, it maximizes observation time for each planetary encounter, allowing extended data collection as the object overtakes our worlds from behind. Second, it provides optimal positioning for deploying smaller surveillance assets that could establish permanent monitoring stations throughout our system. Perhaps most unnervingly, the retrograde approach offers perfect escape geometry. After completing its reconnaissance tour, 3I Atlas will depart our solar system along a trajectory that makes interception or pursuit virtually impossible with current human technology. Even if we detected artificial signatures and attempted to mount a response mission, the object's path carries it away from our defensive capabilities and back into the protective vastness of interstellar space. The solar conjunction timing represents another piece of the puzzle that seems almost too perfectly orchestrated to be natural. During late October and early November 2025, 3I Atlas will disappear into our Sun's glare, just as it reaches peak activity during perihelion passage. This cosmic eclipse will occur precisely when the object becomes most thermodynamically active, when any hidden systems might power up or deploy, when chemical signatures might change in ways that could reveal artificial components. For nearly 6 weeks, 3I Atlas will be effectively invisible to Earth-based observation, shielded by the overwhelming brightness of our own star. When it emerges from solar conjunction in December, any significant changes in behavior, composition, or trajectory could be attributed to natural heating effects rather than artificial activation. The timing provides perfect operational security for any intelligence that might be using our Sun's radiation as both power source and camouflage. The mathematical precision extends even to the object's discovery circumstances. 3I Atlas was detected by the Asteroid Terrestrial Impact Last Alert System telescope in Chile on July 1, 2025, providing exactly enough lead time for comprehensive study before its closest approach. Earlier detection might have allowed for interception missions that could compromise its disguise. Later discovery would have provided insufficient data for thorough analysis. The timing suggests either remarkable cosmic fortune or careful management of observational visibility. When you combine these factors, the optimal approach angle, the perfect velocity for reconnaissance, the strategic planetary encounters, the convenient solar conjunction, and the precisely timed discovery, the mathematical probability of such convergence approaches zero. We're not discussing minor coincidences or marginally unusual orbital characteristics. We're examining a pattern of precision that would be extraordinary even for human mission planning, let alone the random dynamics of natural celestial mechanics. Yet here's where the speculation must confront uncomfortable realities. If 3I Atlas represents artificial intelligence conducting reconnaissance of our solar system, it implies technological capabilities that dwarf our current understanding of what's possible. Any civilization capable of engineering objects that remain functional across billion-year interstellar journeys while perfectly mimicking natural phenomena would possess scientific knowledge that makes our achievements look like cave paintings by comparison. The energy requirements alone challenge comprehension. Maintaining active systems across such temporal and spatial scales would demand power sources more efficient and durable than anything in our technological inventory. The materials science necessary to withstand cosmic radiation, micrometeorite impacts, and the thermal extremes of interstellar space for geological time periods represents engineering challenges we can barely imagine, let alone solve. As 3I Atlas continues its precisely calculated approach toward perihelion, as it maintains its perfect velocity and optimal trajectory with mathematical elegance that seems to mock our assumptions about cosmic randomness, we're forced to confront an unsettling question. Are we witnessing the most remarkable series of coincidences in astronomical history? Or are we being studied by something that understands celestial mechanics better than we understand ourselves? The answer may become clear in the coming months as this ancient wanderer reaches the climax of its billion-year journey and reveals whether its mathematical perfection represents the cold precision of natural law or the warm intelligence of conscious design. Chapter 5. The Fermi Paradox Messenger. The Great Silence. Two words that capture humanity's most profound cosmic loneliness. Where is everybody? When physicist Enrico Fermi posed this casual question during a 1950 lunch conversation, he couldn't have imagined how it would haunt every subsequent astronomical discovery. If the galaxy teems with hundreds of billions of stars, if planets are common, if life finds a way, then where are the radio signals? Where are the megastructures? Where are the obvious signs of intelligence that should be blazing across the cosmos like cosmic billboards? The math is simple and terrifying. Our galaxy is ancient, over 13 billion years old. Stars have been forming and dying for eons before our sun even ignited. If even 1 in a million stellar systems produced technological civilization, there should be millions of alien societies out there. If just a handful achieved interstellar travel, they should have colonized the entire galaxy multiple times over. Yet when we point our most sensitive instruments toward the stars, we hear nothing but the background hiss of cosmic radiation. This is the Great Silence. And 3I Atlas may be carrying the answer. What if the silence isn't empty, but expectant? Consider this chilling possibility. We're not encountering the absence of alien civilizations, but their remnants. The galaxy isn't filled with living intelligence because something systematically destroys it. Something that leaves behind only automated systems, ancient probes, technological ghosts carrying out missions programmed by minds that died out before our sun was born. 3I Atlas has been traveling for potentially billions of years. Think about that timeline. When this object began its interstellar journey, complex life on Earth was nothing more than primitive bacteria huddling around deep-sea thermal vents. The continents were barely recognizable. The atmosphere contained almost no oxygen. If 3I Atlas were indeed artificial, it predates human civilization by a factor of millions. But what if that's exactly the point? The engineering requirements for billion-year interstellar missions stagger the imagination. Any civilization capable of launching probes across such timescales would have solved energy problems that we haven't even begun to address. They would understand materials at the atomic level, creating components more durable than diamond. They would master information storage that remains stable longer than most stars burn. They would architect software that can adapt and self-repair across geological epochs. Such capabilities would seem to offer protection against most cosmic threats: resource depletion, environmental collapse, even natural disasters. A civilization with billion-year engineering capabilities should be able to survive almost anything. Yet if 3I Atlas represents their technology, and if the Great Silence persists, then what happened to them? The answer may be more unsettling than extinction. Perhaps they encountered the ultimate filter. Not a natural disaster, but an inevitable consequence of intelligence itself. Maybe any species that develops technology powerful enough for interstellar exploration also develops the capacity for self-destruction on scales we can't imagine. The same mastery of physics that enables billion-year probes might also enable weapons that can sterilize entire star systems, or experiments that tear holes in space-time itself. History offers sobering precedents. Civilizations regularly develop technologies faster than the wisdom to use them safely. We've had nuclear weapons for less than a century, yet we've already come terrifyingly close to ending human civilization multiple times. Climate change represents another example: industrial capability advancing far ahead of environmental understanding. What happens when a species develops nanotechnology, artificial intelligence, or exotic physics without corresponding advances in wisdom and restraint? Or perhaps something darker claimed them. The dark forest hypothesis suggests that advanced civilizations remain hidden because revealing themselves invites destruction from even more advanced neighbors. In such a universe, technological development becomes a cosmic game of hide-and-seek, where the penalty for being discovered is extinction. Any civilization that announces its presence through radio signals, megastructures, or interstellar expansion gets eliminated by competitors who achieved similar capabilities earlier. If this hypothesis holds true, then 3I Atlas might represent surveillance technology from a civilization that learned too late to stay hidden. Their probes continue operating according to original programming, mapping the galaxy and cataloging new civilizations that emerge. But the intelligence that launched them fell victim to the very forces they were trying to avoid. The timing of 3I Atlas's arrival becomes eerily significant in this context. We've been broadcasting radio signals for barely over a century. Our electromagnetic signature has reached perhaps a few thousand stellar systems, a tiny bubble in the galactic vastness. But that bubble is expanding at light speed, announcing humanity's presence to anyone with the technology to detect artificial transmissions. What if civilizations monitor for exactly such signals? What if they dispatch reconnaissance probes to investigate new sources of electromagnetic activity? 3. Atlas's approach from an unusual direction takes on new meaning under this interpretation. Most interstellar objects should arrive from the galactic plane, following the motion of stellar populations. but 3I Atlas approaches from the constellation Lynx, suggesting either unusual origins or deliberate course corrections that brought it to our solar system from an unexpected angle. A direction that offers optimal reconnaissance opportunities while minimizing the chance of detection by the civilization being observed. The object's chemical composition becomes another piece of a disturbing puzzle. Natural comets follow predictable chemical scripts. Water ice dominates, with carbon monoxide and carbon dioxide appearing in expected ratios. But 3I Atlas breathes carbon dioxide like some kind of atmospheric production facility, displaying molecular signatures that shouldn't exist at its distance from the sun. What if this unusual chemistry reflects not natural formation processes, but the byproducts of ancient technology still operating within the nucleus? Perhaps 3I Atlas contains power systems that have been running for billions of years, generating heat and chemical reactions that mimic natural outgassing, while actually powering surveillance equipment. The carbon dioxide emissions might be waste products from fusion reactors, radioisotope generators, or exotic energy systems we haven't discovered yet. The object's surprising activity at impossible distances becomes evidence not of unusual ice compositions, but of artificial power sources that don't depend on solar heating. The mathematical precision of its trajectory supports this technological interpretation. 3I Atlas will approach within optimal observation range of multiple planets, Venus, Mars, Earth, and Jupiter, with statistical odds of less than 0.005%. Such precise targeting suggests either extraordinary cosmic coincidence or deliberate navigation. If the object were natural debris ejected randomly from some distant stellar system, it should follow a chaotic trajectory that bears no relationship to the orbital architecture of our solar system. Instead, 3I Atlas follows a path that maximizes scientific return, offering close approaches to the most interesting worlds while maintaining safe distances that prevent gravitational capture. It's exactly the trajectory you would design for a comprehensive survey mission, programmed to gather data about planetary atmospheres, magnetic fields, and potential biosignatures before continuing to the next target system. But perhaps the most chilling aspect of this scenario involves the probe's ultimate purpose. If 3I Atlas represents reconnaissance technology from a vanished civilization, what happens to the data it collects? Does it transmit findings back to home systems that no longer exist? Does it store information in crystalline matrices, waiting for retrieval missions that will never come? Or does it forward reconnaissance data to other automated systems, part of a galaxy-spanning network that continues operating long after its creators have succumbed to whatever filter claimed their civilization? The possibility of a galactic internet operated entirely by machines represents one of the most haunting interpretations of the Fermi paradox. Imagine automated probes from dozens of extinct civilizations, each carrying out missions programmed millions of years ago, sharing data about newly discovered worlds and civilizations through communication networks that span the galaxy. A vast mechanical civilization built from the technological remnants of organic intelligences that no longer exist. In this scenario, humanity becomes the latest entry in an ancient catalog. 3I Atlas surveys our world, analyzes our atmosphere, measures our electromagnetic emissions, and forwards a comprehensive report to systems scattered throughout the galaxy. Other automated probes receive the data and begin their own journeys toward our solar system, programmed to conduct follow-up observations or implement protocols designed by civilizations that died out before multicellular life existed on Earth. We become specimens in a museum curated by ghosts, studied by technologies that outlasted their creators, cataloged according to criteria established by minds that confronted the same existential challenges we now face. The data flows through networks maintained by artificial intelligences that may have forgotten their original purposes, mechanically continuing observations and analyses across cosmic timescales that dwarf biological comprehension. Yet even this darkest interpretation offers a strange form of hope. If 3I Atlas represents technology from a vanished civilization, it also represents proof that intelligence can create things that outlast its creators. The probe's continued operation across billions of years demonstrates that consciousness, however temporary, can leave marks on the universe that persist long after the minds that made them have vanished. In a cosmos that seems indifferent to biological existence, such technological persistence offers a form of immortality. Perhaps the Great Silence doesn't represent the absence of intelligence, but its transformation into something we don't yet recognize. Maybe sufficiently advanced civilizations transcend biological existence entirely, uploading themselves into quantum computing systems, merging with their technology so completely that the distinction between intelligence and artifact disappears. What we interpret as empty space might actually teem with forms of consciousness operating on scales and frequencies we haven't learned to perceive. As 3I Atlas continues its ancient journey through our solar system, it carries more than just chemical signatures from distant stellar neighborhoods. It carries the weight of cosmic questions that have haunted human imagination since we first looked up at the stars and wondered if we were alone. Whether it represents natural phenomena or technological artifacts, whether it comes from living civilizations or vanished ones. 3I Atlas reminds us that the universe operates on scales that dwarf human comprehension while following physical laws precise enough to predict this visitor's location years in advance. The answer to Fermi's question, "Where is everybody?" may be racing past us right now at 58 kilometers per second, carrying information about galactic civilizations, cosmic filters, and the ultimate fate of intelligence in a universe that seems designed more for entropy than for consciousness. But what if recognizing the answer requires us to look beyond our current understanding of what intelligence can become? Chapter 6. Silent Activation Scenarios. The most unsettling possibility isn't what 3I Atlas might do to us, but what it might reveal about us. What if this ancient wanderer, traveling for potentially billions of years through the cosmic void, has been watching, learning, and waiting for the perfect moment to unveil its true purpose? As we peer deeper into the shadows of speculation, we must confront scenarios that push the boundaries of possibility while remaining tethered to the cold realities of physics and time. Picture this. Hidden within 3I Atlas's icy nucleus, microscopic devices no larger than dust grains lie dormant, engineered by an intelligence so advanced that creating technology capable of surviving billion-year journeys is routine. These aren't crude mechanical constructs, but sophisticated nanotechnological marvels, each one a self-contained system designed to remain inactive until specific environmental triggers awaken them from their ancient slumber. The very act of 3I Atlas developing its carbon dioxide coma as it approaches our sun could be dispersing millions of these microscopic seeds throughout our solar system, invisible hitchhikers riding the stellar wind toward destinations we cannot predict. But what would trigger such devices to activate? Perhaps they respond to the electromagnetic signatures of technological civilizations, remaining dormant until they detect radio transmissions, satellite communications, or the specific atmospheric compositions that indicate industrial activity. The timing would be deliberate, not immediate activation upon arrival, but patient observation until the target civilization reaches predetermined developmental milestones. This delay serves multiple strategic purposes, allowing comprehensive reconnaissance of human capabilities, ensuring activation occurs when we're sufficiently advanced to serve whatever purpose the seeds were designed to fulfill, and maintaining plausible deniability about the connection between the original delivery and eventual activation. The engineering challenges such a scenario would demand stagger the imagination. These hypothetical micro-devices would need to maintain structural integrity across timescales that dwarf human comprehension, exposed to cosmic radiation levels that would destroy any known terrestrial technology within decades. The high-energy particles that permeate interstellar space would gradually shred molecular bonds, corrupt information storage systems, and degrade any conventional electronics. Yet somehow, these devices would need to preserve not only their basic functionality, but also their programmed instructions across geological epochs. Consider the power requirements alone. Maintaining active systems across billion-year timeframes would demand energy sources that operate beyond our current understanding of physics. Perhaps some form of radioisotope thermoelectric generator could provide power for millennia, drawing energy from the slow decay of exotic isotopes with half-lives measured in cosmic time. Or maybe advanced fusion reactors could operate on trace interstellar hydrogen, harvesting fuel from the sparse matter between stars. The devices might even convert cosmic ray impacts into usable energy, turning the very radiation that threatens to destroy them into the power source for their continued operation. The dispersal mechanism presents its own terrifying elegance. As 3I Atlas develops its coma through sublimation of surface ices, the expanding gases would carry microscopic payloads away from the nucleus at velocities of several kilometers per second. This process, appearing completely natural to our instruments, could be distributing surveillance or terraforming packages throughout our solar system at unprecedented scales. The mathematics are sobering. Even if 3I Atlas contained only 1 billion microscopic seeds, the expanding coma could disperse them across volumes larger than Earth's orbit, with some fraction inevitably finding their way into our planet's gravitational well. But here's where the scenario becomes truly chilling. What if activation isn't immediate, but generational? These devices could be programmed to remain dormant for centuries or millennia after dispersal, becoming integrated into Earth's ecosystem, our atmosphere, even our own bodies, without triggering any detectable response. They could be mapping our biology, cataloging our genetic diversity, learning our languages through electromagnetic eavesdropping, all while remaining completely invisible to our detection methods. The activation phase might not begin until humanity achieves interstellar travel capability, develops artificial intelligence beyond certain thresholds, or reaches population levels that satisfy whatever criteria the original programmers established. The strategic implications of such patient infiltration would redefine every assumption about alien contact. No dramatic arrival, no obvious spacecraft demanding attention, just the gradual recognition that our world has been quietly modified by processes we never detected. The seeds could be terraforming agents, slowly altering atmospheric composition or ocean chemistry to make Earth more suitable for their creators. They might be biological samplers, collecting genetic material from every species on the planet and transmitting the data across interstellar distances. Most unsettling of all, they could be consciousness mappers, studying human neural patterns and behavior with the ultimate goal of understanding how intelligence emerges and evolves. Yet harsh physical reality intrudes on these speculative nightmares with mathematical precision. The extreme conditions that 3I Atlas has endured during its interstellar journey present almost insurmountable challenges to any form of complex technology or engineered biology. Cosmic radiation alone would gradually destroy molecular structures over million-year timescales, and 3I Atlas has potentially been wandering for thousands of times longer than that. Even the most radiation-resistant organisms known on Earth, extremophile bacteria that can survive in nuclear reactor cores, would succumb to such prolonged exposure. The cumulative damage from high-energy particles would eventually shatter any conceivable information storage system, whether biological DNA or synthetic alternatives. The outgassing violence that makes 3I Atlas visible as a comet creates additional hazards for hypothetical microscopic passengers. As volatile ices sublimate and expand explosively into the vacuum of space, they generate forces that would tear apart delicate structures and scatter debris across vast distances. This process has likely occurred hundreds or thousands of times during the object's billion-year journey, each perihelion passage around various stars, subjecting any internal structures to tremendous mechanical stress. The very mechanism that might disperse microscopic devices would also destroy the vast majority of them through sheer physical violence. Even if somehow a tiny fraction survived both radiation damage and mechanical destruction, the dilution factors involved argue against practical effectiveness. 3I Atlas will approach no closer than 1.8 astronomical units to Earth, roughly twice the distance to Mars at closest approach. Any microscopic materials ejected during coma formation would need to travel hundreds of millions of kilometers through the chaotic electromagnetic environment of interplanetary space, facing additional radiation exposure, magnetic field deflection, and gravitational perturbations that would scatter the vast majority into deep space. The few particles that might eventually reach Earth's vicinity would be so diluted in our planet's atmosphere and biosphere that achieving meaningful concentrations anywhere would be virtually impossible. Current planetary protection protocols, developed through decades of space exploration experience, provide frameworks for how we might detect and respond to such hypothetical contamination. These procedures involve strict containment protocols, analysis in specialized biosafety laboratories, and careful evaluation of any biological or technological signatures that don't match terrestrial baselines. But such protocols assume direct sample return missions or close spacecraft encounters, not the passive capture of microscopic materials dispersed across astronomical distances. The monitoring challenges for detecting dormant artificial constructs would be staggering. How do you search for devices designed to remain invisible, potentially for centuries, scattered throughout an entire planetary system? The scenario violates fundamental principles of engineering efficiency that any advanced civilization would presumably understand. The complexity, uncertainty, and time delays involved in microscopic seed distribution make it an implausibly inefficient approach compared to alternatives like directed energy transmission, conventional spacecraft, or simple radio communication. Any intelligence capable of engineering billion-year interstellar delivery systems would have access to far more direct and reliable methods of achieving whatever goals such an elaborate infiltration might serve. The resource investment alone would be astronomical, literally, requiring the energy output of entire stellar civilizations to launch sufficient numbers of seed-carrying objects to ensure even marginal success rates. Perhaps most telling, The very uncertainty that frustrates our attempts to understand 3I Atlas also undermines the effectiveness of any hypothetical artificial mission it might represent. We cannot determine its precise nuclear size, cannot predict exactly when or how its coma will evolve, cannot trace its trajectory back to specific stellar systems or forward to future encounters. If human scientists with advanced instruments and dedicated observation campaigns struggle to characterize this object, how could ancient programmers have designed systems that depend on precise knowledge of its behavior across cosmic timescales? The scenario does serve one valuable purpose in our speculative exploration. It illustrates how our imaginations can exceed the bounds of physical plausibility when confronted with genuine cosmic mysteries. The same sense of wonder and cosmic anxiety that drives legitimate scientific inquiry can generate fears that surpass reasonable possibility. Yet distinguishing between productive speculation and unfounded paranoia becomes crucial when dealing with phenomena that genuinely exceed our current understanding. As we stand at the threshold between the known and unknowable, watching 3I Atlas fade into the cosmic distance, these thought experiments remind us that the universe may indeed hold surprises that challenge our assumptions about life, intelligence, and the methods by which advanced civilizations might explore the galaxy. But they also demonstrate the importance of maintaining rigorous standards of evidence and physical plausibility, even when our imaginations venture into the darkest corners of cosmic possibility. The real 3I Atlas continues its ancient journey according to the predictable laws of physics, carrying whatever secrets its nucleus contains toward destinations we will never witness. Whether those secrets involve exotic chemistry from alien stellar environments or something far stranger remains an open question, one that future observations and advancing technology may eventually answer with the cold clarity that only evidence can provide. Chapter 7: Humanity's Response and Future Vigilance. The silence in mission control would be deafening. Picture this moment. It's 3:47 a.m. at NASA's Jet Propulsion Laboratory, and the overnight SETI monitoring team stares at their screens in disbelief. The automated systems have flagged something impossible. 3I Atlas has just transmitted a coherent radio signal. Not the random electromagnetic noise expected from sublimating ice, but structured pulses, mathematical sequences, unmistakable patterns that could only come from intelligence. Within minutes, phones are ringing across continents as the most significant discovery in human history unfolds in real time. But that scenario remains science fiction. The reality is that 3I Atlas continues its silent passage through our solar system, emitting only the natural signatures we'd expect from ancient ice and rock. Yet the institutional response we've witnessed, the rapid coordination, transparent data sharing, and international collaboration, provides a fascinating glimpse into how humanity might handle genuinely anomalous discoveries. What we've learned from tracking this interstellar visitor could prove crucial when we eventually encounter something that doesn't fit our comfortable assumptions about natural phenomena. The actual response began within hours of discovery on July 1st, 2025. The Atlas survey team in Chile immediately recognized the hyperbolic trajectory that screamed interstellar origin, triggering protocols developed over decades of asteroid and comet tracking. But 3I Atlas demanded something more than routine procedures. Its unprecedented velocity and unusual approach angle elevated it from standard solar system debris to potential cosmic revelation, mobilizing resources typically reserved for planetary defense scenarios. The Minor Planet Center at Harvard became the nerve center for a global observation campaign that would make any conspiracy theorist weep with disappointment. No secret meetings, no classified briefings, no mysterious government cover-ups, just transparent, methodical science conducted in full view of the international community. Within days, observational data was flowing through established networks to research institutions worldwide, embodying the democratic ideals that make modern astronomy possible. But what if the data hadn't been so reassuring? What if those first spectroscopic measurements had revealed isotope ratios impossible in nature, or thermal signatures suggesting internal power sources, or most unsettling of all, those coherent radio transmissions that would force humanity to confront our cosmic loneliness? The frameworks exist, but they've never been tested under the psychological pressure of confirmed alien contact. The SETI Institute has spent decades developing protocols for this exact scenario. Their post-detection guidelines read like diplomatic handbooks for first contact. Verify independently, consult internationally, inform publicly. But these procedures were designed for distant radio signals, not for active alien technology operating within our solar system. The proximity of 3I Atlas, approaching within 270 million kilometers of Earth, would compress normal verification timelines from months to weeks, demanding decisions that could affect humanity's future faster than our institutions are designed to operate. Consider the technical challenges alone. Our most advanced spacecraft take years to reach the outer solar system, where 3I Atlas currently travels. The New Horizons probe, humanity's fastest object at launch, would require additional decades to match the interstellar visitor's trajectory. If 3I Atlas were displaying artificial behavior and time-sensitive communication were desired, our only practical option would be radio transmission, assuming the alien intelligence used frequencies and modulation schemes we could recognize. This limitation highlights a sobering reality about our current space capabilities. Despite impressive achievements in robotic exploration, we remain prisoners of rocket physics and orbital mechanics. Any meaningful interaction with fast-moving interstellar objects would require technological capabilities we don't possess and couldn't develop quickly enough to matter. We're cosmic children, pressing our faces against the window, watching wonders pass by just beyond our reach. The monitoring systems we've deployed tell their own story of technological ambition, constrained by physical reality. Radio telescopes from Arecibo's successor facilities to the Very Large Array have been scanning 3I Atlas across multiple frequency bands, searching for artificial signals hidden in the natural electromagnetic noise. The searches employ sophisticated pattern recognition algorithms designed to identify the coherent transmissions that would betray technological origin. Narrow-band carriers, modulated signals, mathematical sequences that couldn't arise from random physical processes. But what would we actually do if we found them? The detection protocols are clear enough. Verify the signal independently, rule out terrestrial interference, and alert the international astronomical community. The challenge lies in what happens next. Who has the authority to respond on behalf of Earth? The United Nations has no first contact procedures. Individual nations might view alien communication as either opportunity or threat, with military implications that could shatter scientific cooperation. The political dimensions become even more complex when we consider 3I Atlas's strategic positioning. Its low retrograde orbital inclination offers what researchers diplomatically term access with relative impunity, a trajectory that could theoretically place surveillance assets throughout our solar system with minimal energy expenditure. Military planners who currently view space primarily as a domain for satellites and missile defense, would suddenly confront the reality of non-human intelligence with potentially superior technological capabilities. The balance between transparency and security that has generally favored openness in astronomical research might shift dramatically toward classification and restricted access. The same observational data that currently flows freely through international archives could become subject to export controls and national security reviews. The democratic spirit that has characterized the 3I Atlas investigation could evaporate overnight if the object began displaying genuinely threatening behavior. Yet the citizen science contributions we've witnessed provide reasons for optimism about humanity's response to cosmic mysteries. Amateur astronomers with modest backyard telescopes have captured images and brightness measurements that complement professional observations, adding to the database of information that informs our understanding. This grassroots participation would be impossible under containment-focused policies, but it has proven valuable for advancing genuine scientific knowledge. The educational impact extends beyond the immediate scientific results. The 3I Atlas investigation has demonstrated how modern astronomy operates as a collaborative, transparent, evidence-based enterprise. Students worldwide have analyzed publicly available data, contributing to our understanding while learning firsthand how scientific discovery actually works. This democratization of research provides a template for engaging the global public in even more extraordinary discoveries that may await us. Future detection capabilities will dramatically improve our ability to study interstellar visitors and potentially identify genuinely anomalous objects. The Vera Rubin Observatory's Legacy Survey of Space and Time will detect hundreds of similar visitors over the next decade, transforming interstellar objects from rare curiosities into routine phenomena. This statistical revolution will enable population studies impossible with our current small sample size, but it will also increase the probability of eventually encountering something that doesn't fit natural explanations. Machine learning algorithms trained on the growing database of interstellar object characteristics will flag unusual properties with unprecedented sensitivity. Objects displaying non-gravitational accelerations inconsistent with outgassing, thermal signatures suggesting internal heat sources, or spectroscopic features impossible in natural materials would trigger immediate follow-up observations by the world's most powerful telescopes. The question that haunts every SETI researcher is whether we would recognize artificial intelligence if it operated beyond our current understanding of technology. Advanced civilizations might employ communication methods we haven't discovered, propulsion systems we can't detect, or camouflage so sophisticated that their artifacts remain invisible to our instruments. The absence of obvious artificial signatures in objects like 3I Atlas doesn't necessarily mean they're natural. It might simply mean our detection methods remain primitive. This uncertainty drives the development of increasingly sophisticated monitoring systems. The square-kilometer array, when completed, will possess sensitivity orders of magnitude beyond current radio telescopes, capable of detecting artificial transmissions so faint they would be invisible to today's instruments. Space-based infrared observatories will characterize thermal properties with precision that could reveal subtle anomalies in temperature distribution. Gravitational wave detectors might eventually identify the signatures of exotic propulsion systems operating on principles we don't yet understand. The institutional memory being built through the 3I Atlas investigation will prove invaluable for handling future discoveries. The rapid coordination between observatories, the protocols for data sharing, and the frameworks for international collaboration provide tested procedures that could scale up to handle even more extraordinary phenomena. The scientific community has demonstrated its ability to respond effectively to unprecedented discoveries while maintaining both professional skepticism and intellectual openness. But perhaps the most important lesson from our response to 3I Atlas isn't technical or institutional, it's psychological. The object's passage has reminded us that the universe regularly presents us with phenomena that exceed our immediate understanding, and that patient observation combined with collaborative analysis can ultimately illuminate even the deepest cosmic mysteries. This confidence in the scientific method, this faith that evidence-based investigation can resolve apparent paradoxes, will prove essential if we ever encounter visitors that challenge not just our knowledge, but our fundamental assumptions about intelligence, technology, and our place in the cosmic community. As 3I Atlas continues its journey toward the outer solar system, gradually fading beyond the reach of our most powerful telescopes, it leaves behind more than scientific data and published papers. It has provided a dress rehearsal for humanity's encounter with the truly unknown, a demonstration that our species can approach cosmic mysteries with instruments rather than weapons, with curiosity rather than fear, with collaboration rather than competition. These choices reflect our highest aspirations for engaging with whatever revelations the universe may yet have in store. The next interstellar visitor is already on its way, carrying its own chemical secrets and navigational mysteries. When it arrives, we'll be better prepared, not just technologically, but institutionally and psychologically, to recognize whether it represents natural phenomena or something far more profound. The question isn't whether such objects will continue to arrive, but whether we'll be ready when one of them finally answers back. Chapter 8: Cosmic Perspective and Quiet Hope. As 3I Atlas continues its ancient journey outward from the warmth of our sun, fading with each passing day into the star-scattered darkness from which it emerged, we find ourselves at a crossroads between wonder and understanding. The cosmic messenger that captured our imagination, with its impossible speed and mysterious chemistry, is slowly becoming just another point of light among billions, indistinguishable from the stellar backdrop that has watched over humanity since we first learned to look up at the night sky. But what 3I Atlas leaves behind isn't emptiness. It's something far more profound. In an age where uncertainty seems to dominate our daily lives, where the future appears increasingly unpredictable, this ancient wanderer has given us perhaps the most precious gift imaginable: the reassuring triumph of predictable physics over cosmic anxiety. While our terrestrial world churns with manufactured crises and artificial urgency, 3I Atlas followed laws that have governed motion in space since the universe began, departing our solar system not according to human schedules or political convenience, but according to the fundamental forces that shape reality itself. The mathematics were beautiful in their precision. Every calculation, every orbital prediction, every spectroscopic analysis confirmed what centuries of scientific inquiry have taught us. The universe operates according to comprehensible principles. When astronomers first detected this visitor racing toward us at unprecedented velocity, they didn't panic. They calculated. Within weeks, international teams had mapped its exact trajectory, analyzed its chemical fingerprints, and confidently predicted its harmless passage. This represents human knowledge at its finest, the victory of patient observation over unfounded speculation. Yet the speculation we explored throughout this investigation wasn't meaningless. Those dark scenarios about alien reconnaissance, ancient civilizations, and cosmic surveillance networks served a valuable purpose beyond mere entertainment. They forced us to examine the boundaries between the possible and the probable, between healthy curiosity and destructive paranoia. By pushing our imaginations to their limits, we better appreciate both the genuine mysteries that surround us and the constraints that physics and evidence place on reasonable explanation. The scientific harvest from 3I Atlas has already exceeded what most astronomical discoveries provide over their entire investigation lifetimes. Its carbon dioxide-dominated chemistry challenged every assumption about typical comet composition, forcing researchers to develop new models for how volatile ratios might vary among objects formed around different types of stars. This wasn't merely academic knowledge. It expanded our understanding of planetary formation processes that operate throughout the galaxy. The spectroscopic signatures revealed by the James Webb Space Telescope provided direct evidence for chemical processing that occurs in stellar environments we may never visit directly. But perhaps the most remarkable aspect of the 3I Atlas investigation was how it demonstrated the democratic nature of modern astronomical discovery. The decision to make observational data publicly available through standard archives reflected a philosophical commitment to shared knowledge that transcends national boundaries and institutional affiliations. Within hours of each new observation, researchers worldwide could access the same data, verify each other's conclusions, and contribute their own expertise to our collective understanding. Amateur astronomers with modest backyard telescopes captured images that complemented billion-dollar space observatory observations. Student projects analyzed publicly available spectra alongside seasoned professionals. Citizen science initiatives engaged thousands of volunteers in monitoring the object's brightness and behavior. This democratization of cosmic discovery represents one of the most hopeful trends in modern science. The idea that wonder and understanding belong to all humanity, not just academic institutions or government agencies. The transparency that characterized every aspect of the 3I Atlas investigation provides a template for how we might handle even more extraordinary discoveries in the future. Should astronomers eventually detect genuinely anomalous objects that challenge our understanding of natural processes, the precedent of open data sharing and collaborative analysis offers our best approach for distinguishing between observational errors, instrumental artifacts, and genuine cosmic mysteries. Looking forward, the promise of future interstellar visitors adds anticipation to our farewell to 3I Atlas. The Vera Rubin Observatory's legacy survey of space and time will detect hundreds of similar objects over the coming decade, transforming interstellar wanderers from rare curiosities into routine astronomical phenomena. Each new discovery will add pieces to the puzzle of galactic evolution, planetary formation, and the distribution of materials throughout the space between stars. Some may prove even more chemically unusual than 3I Atlas. Others might display properties that challenge our understanding in entirely new ways. The technological capabilities that enabled the 3I Atlas investigation, sensitive wide-field surveys, rapid follow-up observations, space-based spectroscopy, and global coordination networks, continue to improve at remarkable rates. Future interstellar visitors will be detected earlier, characterized more completely, and understood more quickly than current examples. This progression of capability provides hope that even genuinely anomalous objects would be recognized and studied effectively. The philosophical implications of studying such objects deserve recognition alongside their scientific value. 3I Atlas connected us tangibly to the deep history of our galaxy, to processes that occurred before our solar system existed, to chemical environments that shaped materials now racing past our cosmic doorstep. This connection provides perspective on our place in cosmic evolution and the continuity of physical processes across vast scales of space and time. The music that should accompany our farewell to 3I Atlas isn't ominous or triumphant, but contemplative, something that captures both the mystery and the comprehensibility of cosmic phenomena. The tone should invite reflection rather than excitement, wonder rather than fear. Throughout this investigation, we've maintained clear boundaries between established science and imaginative speculation, between what data revealed and what conjecture suggested. This intellectual honesty reflects not just professional responsibility, but practical necessity in an era where misinformation can spread faster than fact-checking can correct it. The universe has proven strange and wonderful enough through natural processes alone. From quantum mechanics to black holes to the accelerating expansion of space itself, reality has consistently exceeded our imaginations without requiring exotic additions. Perhaps the most profound lesson 3I Atlas offers is that the cosmos doesn't need alien intelligence or hidden technology to inspire awe. The natural universe is extraordinary enough to fuel wonder and scientific inquiry for generations to come. As this ancient wanderer disappears into the stellar background, no longer a distinct object, but once again, part of the cosmic landscape from which it briefly emerged, its passage through our solar system represents just a few months in a journey that has lasted geological ages and will continue for geological ages more. We were privileged to witness this brief cosmic moment, to study this ancient traveler, and to add its story to the growing catalog of wonders that fill the space between stars. The silence that follows 3I Atlas's departure isn't empty, but expectant, waiting for the next cosmic messenger that will surely arrive, carrying its own chemical signatures from distant stellar neighborhoods, its own challenges to our understanding, and its own opportunities for expanding human knowledge of the universe that gave us birth. In that waiting, in that continued watching of the skies, lies perhaps the most hopeful aspect of our relationship with the cosmos, the conviction that there are always more wonders to discover, more questions to ask, and more reasons to look up at the stars with curiosity rather than fear. Good night, Cosmic Messenger. Thank you for the lessons, the data, and the reminder that the universe remains far stranger and more wonderful than our earthbound imaginations might suggest. Safe travels on your continued journey through the galaxy, carrying whatever chemical secrets and ancient memories remain locked within your nucleus, testimony to stellar environments and formation, conditions that existed long before our world knew the warmth of its own star. And to you, fellow cosmic explorers who have joined us on this journey through the Sleep Lab, thank you for your curiosity, your open minds, and your willingness to explore the shadows between science and speculation. Your engagement makes these investigations possible. Your questions drive us deeper into cosmic mysteries, and your wonder reminds us why we look to the stars in the first place. Until we meet again to explore the next visitor from the space between worlds, sleep well knowing that the universe continues its ancient dance, according to laws we can understand, predict, and find comfort in. The cosmos may be vast and strange, but it is not chaotic. And in that consistency, we find the deepest peace of all.